Hooray! Okay, cool. So hopefully it'll behave now. So, okay. So we're going to see here that this is one type of isometry that we had, which is cis and trans. We're going to see that these two are opposite sides of each other. We call this the trans isomer. This one will be the cis isomer. They're on the same side. And this is going to be a little bit easier to see in square planar complexes. For example, if we had something like, I don't know, this is a bad example. Let's not use iodine. Let's use ammonia. Okay, so with this, with a square planar complex like this, it's a little bit easier to see. So remember, square planar, we have two going backwards, two going forwards. They're all in the same plane as each other. Here, if we're looking at the chlorines here, we're going to see these two chlorines are on the same side as each other. So this will be a cis isomer. And this one has the chlorines on the opposite side. So that's going to be the trans isomer there. And so hopefully that's a little bit easier to see in a square planar complex like this, where you can see they're 180 degrees apart versus 90 degrees apart. So, it's the same idea here. We had kind of 90 degrees here versus 180, so we're going to see that those will have different sides. So, cis-trans stuff. As Kevin has pointed out, you can't have this in tetrahedral ones because everything is the same angle no matter what. Where we had octahedral, we have 90-degree angles around, but there's also kind of that 180 if you go straight down. With tetrahedral, everything is 109.5, right? So we don't have anything that we can't have as cis or trans. This is not going to work. So if we try and do something here, oops, that one. Okay. If we try and do something like this, these are not going to be cis-trans isomers. I guess I need to make that one actually 3D. The reason is because the angle in between them is the same still. So we've just kind of rotated our molecule a little bit. So this is a different type of isometry that we're going to see. But for our purposes, these are not geometric isomers. So there's no geometry here that we can change. Can't change any angles. So these are not going to be geometric isomers. In fact, these will just be structural isomers. So they're actually, no, this is the same molecule, just rotated a little bit. If we were to rotate it along the cobalt-fluorine axis, we would be able to get our original molecule back. So these are, in fact, the same molecule. So they're just rotated of each other. So we might call them rotamers or something, but they're really not isomers. They're the same molecule. They're identical to each other. So we're going to say that's not the case here. So no matter how we try and rotate our cis-trans isomers, though, we can't get them to be the same thing as they were before. So those are going to be a special type that we have. Another type we have, though, are what are called linkage isomers. And these will be ones that where you'll have different atoms in the same ligand that can form the dative bonds. For example, if we take a look at cyanide, we of course have the minus charge here, we could bond to a metal from either side of this molecule, or ion, right? We could say, okay, here's our cobalt or whatever, and we're going to connect it to the carbon side. However, if it just so happened, we could end up connecting it to the nitrogen side instead. These are called linkage isomers. So they have the same ligand, but they're just bound different ways. So typically we're going to see it's going to be the carbon that's going to be doing this, but sometimes you'll have the nitrogen bonding instead. And there's just other reasons that might happen. Maybe you have other negative things around. Since the carbon does have the negative charge on it, that can kind of force the nitrogen to bond instead. So these are just called linkage isomers. But they're less common, and it's only going to be with things that have the potential to bond in multiple areas. Another one would be thiocyanate. You can bond on either the sulfur or the nitrogen, or nitrite. You can bond from either the nitrogen or one of the oxygens. So all of these are going to be able to have that kind of, be able to form linkage isomers. But they're kind of less important. So we don't care about them. All right, however, one that's very important are stereoisomers. An example of a stereoisomer would be something like this, where you need a pair, of course. This would be a pair of stereoisomers. So we note they all have the same ligands, they're all bound the same way. Technically this would be a 1 minus ion, if cobalt is going to be its usual +3. All I've done is switch two ligands here, right? I swapped their positions. But if we look here, these are actually just going to be mirror images of each other. If we were to try and rotate them, you're going to try all you can, try rotating this way, up and down, whatever. No matter how you rotate these, you cannot get them to be identical to each other. These are what we call non-superimposable mirror images of each other. They're like your hands. This is kind of the classic example. Your hands are non-superimposable mirror images of each other. If you were to take your right hand, put it in the mirror, it looks like your left hand does, right? But your right and left hand, no matter how you try, you cannot get them to be exactly on top of each other where they'll line up perfectly. So note my thumb and pinky are offset. The middle finger kind of lines up nicely, but the rest don't, right? So we're going to see that just as your hands are mirror images of each other, and you can't superimpose them, this is the same thing with molecules, certain molecules. And these would be what are called stereoisomers. So we're going to see that these will be something that we're going to talk about. We'll have an entire chapter on these in OChem. The reason being that in biological systems, especially with drugs and enzymes, typically only one of these will be able to react in the way that you want it to. For example, there was a drug back in the 60s called thalidomide, which was used to treat morning sickness. But only one of these stereoisomers that it had, so imagine just two things are switched. They're called enantiomers that way. Only one stereoisomer actually had the effect of treating morning sickness, but the other stereoisomer ended up causing horrible, horrible birth defects. And so it was kind of this, horrible tragedy where they had just thousands of I don't want to say defective babies, but defective babies that had been it's kind of like not really a generation, but within a couple of years they had noticed this, and that was a big problem. So here, let's see. Yeah, so you're gonna see that with many drugs that you deal with, you'll have isomers that have either opposite effects of each other, or one will have no effect, the other will have the effect you want. And so you'll see that these will be very common for us. For example, all of the sugars that our body can digest are D sugars, so they'll rotate light to the right. We'll talk about light rotation in a bit. But we cannot digest L sugars. Although they will taste the same to us, we just can't digest them. We don't have the enzymes. If they're just flipped around, we can't do it. If they have their mirror images of each other, we can't digest them. With amino acids, we use L amino acids. 19 of our 20 amino acids have stereoisomers, so we must only use L of those. They rotate light to the left. So thalidomide's a little bit of a bigger molecule, but suffice it to say that it's just here. I'll go ahead and look here. So it's a good example. Why not? And then we had the you do not need to know this molecule, but this is the thalidomide. If you swapped these two, the H and the succinimate here, you would end up getting the thalidomide that causes the horrible defects. I forget which one of these was the good one and which one was the bad one, but suffice it to say, the only thing that's different between these two is this one carbon here. And all that's different about them is that they have one on a wedge, one on a dash for the either the hydrogen or the succinimide there. And that's what caused these horrible birth defects. So just having it point one direction versus another, having the wrong mirror image can have drastic problems. You'll see like ibuprofen the same way. Usually you'll get both what are called S and R, or sometimes you'll call them D or L. Usually it's S and R though. One of them will have the effect of ibuprofen that you want, the headache and typical NSAID activity. The other one just doesn't do anything. So basically half the ibuprofen you take does nothing. So you're just taking it for no reason. So with drug design, there's a great deal of research going into chiral catalysts and that sort of thing. I don't want to say chiral. Catalysts that will force you to get only one isomer instead of both out. So typically you're going to see in chemistry that you'll end up with a mixture of isomers, but the more you can do to kind of get just one, the better, especially in pharmaceuticals, because they can have drastic, terrible effects otherwise. So, yeah. So this is thalidomide here. But suffice it to say, bad things can happen if you have the wrong image. Suffice it to say, though, the easiest way to look at these, in a tetrahedral one at least, is the easiest. If you have 4 different things attached to your central atom, it's going to have a stereoisomer for something that's tetrahedral. For something that is not tetrahedral, like an octahedral complex, you can have these sorts of isomers as well. Classically, people use the example of having 3 ethylene diamines on a cobalt, or rather some octahedral center. These would also be, as you can see, they're mirror images of each other, right? Here's your mirror They are the opposite of each other. And no matter how you try to rotate them, you're not going to be able to stick them on top of each other. So these are also stereoisomers of each other. Molecules that display stereoisometry are called chiral. So chiral, so it's a hard CH sound. So we would say that this cobalt or triethylene diamine cobalt 3 is going to have it's going to be a chiral molecule or chiral ion, because you can arrange these in such a way that you can't overlap them no matter how you try to do so. And so they're going to form mirror images of each other that you cannot superimpose. So those will be chiral. What's interesting about these is that chiral molecules rotate light. So it's interesting stuff. So light, perhaps as you know, goes in all different directions all the time. But here's our light, by the way. It's a little sun. It's spitting off light rays in all directions all over the place. We're going to see that, you know, they're going to be rotated in all these different ways. But if we pass it through a polarizer, so with this you have light rays going all over the place in all different directions. Some of them are, you know, 90 degrees, some of them are tilted slightly or that way or whatever. They're all just tilted all over the place. If you pass them through what's called a polarizer, you only get one kind of angle out of light. And if you pass it through a chiral molecule, or a solution of chiral molecules, so let's say that this is gosh, it's so hard to show this in my terrible drawing skills of 2 dimensions. Suffice it to say that, let's say this is going just up and down. Okay, you know what? Let's just find a better picture of this because I can't draw. Let's see, chiral molecule rotating light. Let's see if we can't get a nice picture of this. Yeah. Okay. So let me pop open to Google here so we can see it in better drawing in multiple dimensions here. So is this going to be a good one? Yeah, this is actually, I think this is a better one. Okay, let's take a look at this. Oh, these images are tiny. I don't want this image anymore. Okay, suffice it to say, you've got your light going in. It's going just straight up and down, we'll say. Straight up and down as you pass through this polarizer. You put it through your solution of chiral molecules, and you end up tilting your axis of light around. So these types of molecules that are chiral will affect light because they can absorb light in certain ways. And so when they re-emit it, they'll spit it out at a particular angle. And what's interesting is that stereoisomers, here I'm going to just, it's not bent like this, but here, let's say it comes like this now. I've rotated it 90 degrees or something. I'm sorry, I'm a terrible artist. Okay, let's just say it's rotated. If it rotates to the right, it's called dextrorotary. Dextrorotary? I feel like I'm making this word up. Whatever. Or a D isomer rotates light to the right. And a levatorotatory or L isomer rotates to the left. Rotates light to the left. So something like glucose, glucose, this is D-glucose here. Will rotate light to the right. I'm going to make up a number. Let's say it rotates 17 degrees to the right. Its opposite, what's called an enantiomer, which is going to have these hydroxys on the opposite side, is L-glucose. This one will rotate light negative 17 degrees, whatever it happens to be, whatever the number is. That number will be unique for every molecule, so all glucose and all concentrations will always rotate light 17 degrees. I'm again making up that number, I don't know what it is. The D-glucose will always rotate it 17 degrees to the right. L-glucose will rotate it 17 degrees to the left, or some might say negative 17 degrees. And so the two of these will rotate the opposite way. If you have a mixture of them, half of them will rotate to the left, half of them rotate to the right. They'll cancel each other out. There will be no rotation overall if you have a mixture of them. And you'll just have your plain light going through. But if we were to take, say, a sample of our blood, which would have D-glucose in it, it would rotate light to the right, assuming nothing else in our blood is chiral, which is not true. But that's what we're looking at here. Note these are called enantiomers. Let's not worry about enantiomers. We'll talk about that in OChem. So that's not something we're going to need to worry about. So suffice it to say, the way you arrange your stuff in these complexes matters. So sometimes you'll have ones that will be chiral, they'll interact with light, they may interact with other things, and so they'll just behave a little bit differently. All right, but enough about that. That's something we'll talk about in OChem more, so you can kind of put it to the side. However, something that will be important here is molecular orbitals, or rather atomic orbitals, in complexes. Let's move on to other things. So if we're going to take a couple of example molecules here, let's say actually let's make it okay, let's look at these two complexes. We're going to see that this one here is going to be paramagnetic, and this one is diametic. Let's try that again. Diamagnetic. And so, what the hell's going on here? They both have cobalt 3+. Let's take a look at what's actually happening with these and see if we can't figure out an explanation of what's going on here. So these would both be octahedral complexes. They both have 6 ligands, right? So let's take a look at the fluorine one first. Okay, this is our fluorine complex. It's going to be, we have a cobalt 3+ in there, so this is hexafluorocobalt 3. If we look at what's happening here, if we're told this is paramagnetic, well, that means there's got to be unpaired electrons in here, right? Paramagnetic things mean unpaired electrons. if we think cobalt 3 plus, where is cobalt on our periodic table? Let's see. I've got it here somewhere. Cobalt is 1, 2, 3, 4, 5, 6, 7th in the row here. So we have, let's see, we're going to have lost 2 s electrons, and we're going to end up losing 1 d electron. So we have a d6 electron configuration, right? So, nope, too many times. If we're expecting to do the electron configuration for this cobalt 6 plus, well, clearly we have unpaired electrons here, yes? So we're expecting this to be paramagnetic. And lo and behold, it is. Cool. Let's not worry about that then. Let's look at the other one. Okay. If we look at this one, though, look, it's cobalt 3 plus. It has 6d electrons. And since it's exactly the same, electron configuration-wise, we would expect this to be paramagnetic as well. But we're going to see that this one is diamagnetic. So experimentally, this one is found to be repulsed by a magnetic field instead of attracted to it, right? And so, this is experimentally done. So, that tells us that these 6d electrons actually must be paired off, right? So we actually have, oops, something like this happening here. And so, what gives? This isn't what we learned. We learned, you know, Hund's rule told us that we're going to put, and the Hund's rule, yeah, tells us that we're going to put 1 electron in each orbital because they're degenerate, they're of equal energy to each other, and then we're going to pair them off afterwards. However, clearly, because these have formed pairs, these cannot be degenerate orbitals, so they can't have the same energy as each other than these ones. And we're going to see that this leads to something called crystal field theory. And so if we want to take a look at the orbitals or the shapes that d orbitals take, remember we have 5 d orbitals, right? And they all have their fun little names here. If we have our XYZ, I'm going to just copy this. Oh, I don't want that. Okay, there we go. Oh no, poor dz squared will go somewhere down there. Oh, go away. So a dxy orbital has its lobes in between the x and y. A dxz has its orbitals in between the x and the z. Let's see, how am I going to draw this? Okay, between x and z, and then, so there we go. I'm terrible at drawing these, I'm sorry. We'll look at better pictures soon, don't worry. And the one, oh, I'm sorry, this should be YZ. YZ will have them like that. All right, but again, tilted 3D, sorry, terrible at 3D. What's important to notice about x squared minus y squared, though, is that one has them along the x and y axes. So its lobes are along the xy plane. And dz squared is that kind of weird looking one. It's pointing along the z-axis, and it has that kind of ring around it as well that goes a little bit into x and y. Here, let's... Or if we were to look at, very nice images, look at these are beautiful. You can see for the xy, they're in between the x and y axes. For xz, they're in between x and z. For yz, they're going to be in between y and z. And if we look here, x squared minus y squared has them in the same lines as the x and y planes. And then the dz squared has that kind of one kind of p orbital looking thing on the z-axis and kind of the donut around it. So with that in mind, if we try and consider an octahedron, oh gosh, I'm going to see. All right, is that, how do I even draw an octahedron? Let's see. Hold up, let me do some practice drawing here first. No, that's horrible. I don't even know how to draw an octahedron. Suffice it to say, though, if we look at kind of where these ligands are going to line up when we put them on, so if we say we're going to take our cyanides here, we're going to say, okay, well, we have our x-axis here, our y-axis here, and our z-axis here, going up and down. Looks horrible, right? Suffice it, but if we take a look at some of these orbitals, I'm going to just draw one. If we take, for example, the, let's say xz, the one in between x and z, and let's see, the other one's going to be kind of in the back there, and this is going to be in the back there. If we take a look at that one, we can see that these orbital lobes are going to be in between where the ligands lie. But I'm going to just erase this disaster. I'll show better pictures on Google because, again, I'm terrible at 3D drawing. But if we look at something like the xy one, or x squared minus y squared, rather, notice that our d orbitals line up pretty much with the ligands. And we're going to see with the z squared, we're going to have that lining up with the vertical axis and then a little bit with the rest of it. And so we're going to see that because the dx squared minus y squared and dz squared orbitals kind of they're going to be physically closer to the ligands. There is some repulsion there between the d electrons in the metal and the lone pairs from the ligands. So if you can imagine, here's our z squared, here is our cyanide. It has its own lone pair orbitals. Those are going to kind of clash a little bit. However, if we look at something like that xz from before, we have our, I'll make them the same distance. And we have some more over here. Well, suffice it to say, these are going to be farther apart. So this is going to have less repulsion here. This might be the dxz, for example. This is dz squared. But the whole point of this is, because of that, dx squared minus y squared and dz squared are higher energy than the other three. So what you normally have as your 5d orbitals, you actually will split them into two groups here. So you have these two orbitals, the higher energy ones up here. So here's our energy. This will be xy, yz, xz. Those three will be degenerate with each other, the same energy. And we're going to have the other two orbitals are going to be higher energy because of that repulsion that they're going to experience with the ligands. And we're going to see that the energy difference here, we usually just represent as delta, is called the crystal field splitting energy, or we just call it splitting energy. This is going to be what's responsible for those different colors of light, by the way, is the transitions from these lower ones to the higher ones. But let's look at this further. So we're going to see that that's kind of one option that we're going to see. We're going to see, depending on the magnitude of that splitting energy, there's also an energy cost for pairing electrons off. Remember, we don't want to pair electrons because it's going to force one to reverse its spin. There's a little bit of energetic cost associated with that, which is why we normally fill orbitals singly before we start pairing them off, because that's a little bit higher energy to start pairing. We're going to have to compare these two. I don't know, what shall we call this one? I don't know, we don't really have a name for this one, but anyways, whichever one wins, whichever is going to be higher, will determine where the electrons go. We're going to see that if you have a very high splitting energy, so if you have a large energy difference between these two, and let me actually exaggerate this. Let's go ahead and make this even farther down. If you have a very high difference in energy here, you are going to pair them off before moving up. So you will end up, in fact, getting your 6d electrons from this particular cobalt complex will stay down there. This is what's called a low spin state due to high splitting energy. Conversely, if your thing is low, if it's low like this, then you will be filling them normally one each, and then you'll start pairing off later. So if your splitting energy is low, we get what's called a high spin state. So it just depends who's going to win. There's that energy cost for pairing electrons off, but there's also the energy cost for having these d orbitals interacting with your ligands. So it just depends whichever one's going to be bigger. And we are going to see that delta is determined by the ligands. And so we're going to see that we have a Spectrochemical Series which I've posted in Discord already for us earlier this morning. Let me pull it up. It's going to tell us kind of the order of our low splitting energy ligands to high splitting energy ligands. So, for example, we're going to have our let me just put a couple of these out. I don't know, F minus H2O, ammonia. Okay, so there's a couple of them. There's the rest of the list is there too. We're going to see that things on this side have high splitting energy, and they're going to cause low spin states that are going to be more likely to be diamagnetic for our cobalt at least. So because the cobalt 3 plus has 60 electrons, we're going to have 6 electrons down in the lower one. These will have low splitting energy, and they will typically cause high spin states. And this would be an example of a paramagnetic cobalt 3 plus. All right, so we're going to see, it just depends what your ligands are, how they're going to interact with those d orbitals. Some of them that tend to cause these low spin states have high splitting energy, so they will very strongly interact with those d orbitals, so there'll be a lot of repulsion, causing a large energy difference between the orbitals. But something like iodide will have a low splitting energy. It's not going to split it very much overall, and you're going to therefore be able to still singly fill your electrons before pairing them off. And so you'll end up getting, for example, because we are going to see, by the way, I usually kind of draw the cutoff around water. So usually for rule of thumb for octahedral complexes, if you're on the ammonia side and up, you're going to be low spin. If you're on the fluoride side down, you're going to be on the high spin, roughly speaking. So water is right about in the middle, roughly speaking. So it is going to be different for every single atom that you're looking at for the central atom, so it's kind of hard to make that distinction, but suffice to say water is kind of that middle area, where to the right of it we have higher splitting energy, and to the left we have lower splitting energy. Alrighty. We're going to see that we can also detect by color. So the energy associated by moving an electron, so let's say we have our cobalt 3 plus here. It's got its 2 higher energy orbitals there. We can give it some light, and we can promote an electron up to the higher state. and then it can relax again and spit out some more light, right? We're going to see that, of course, this wavelength of light will be proportional to the energy of the light, which will be proportional to our splitting energy. So remember, just like when we talked about any sort of atomic transitions, flame tests, that sort of thing, we see that the wavelength of light that is going to be interacting with your compound is proportional to the splitting energy. So we're going to see putting different ligands on the same metal can cause your metal to have different colors. So here we go, color time. We're going to see that we have our three primary colors here. Hopefully you remember from painting or whatever. If we mix blue and yellow, we get green. If we mix red and yellow, we get orange. And if we mix red and blue, we get purple, right? Remember that the color that we see as humans, the color we interpret, is the light that's being reflected the most. That also means that the light that is being absorbed is the opposite color of what we're seeing. For example, if we see a purple complex, that means yellow is strongly absorbed. Because in white light has all the different wavelengths, right? If all the yellow is taken away, we're going to see more of the opposite of that color. That's what our eyes interpret. So we're going to see that if you kind of look at this color wheel, as it were, the opposite colors are just indicated being the opposite side of this circle. So red and green are opposites, blue and orange are opposites, purple and yellow are opposites from each other. And so whichever one you're seeing, it's the opposite light that is going to be absorbed. And we're going to see remember, as your energy increases, your wavelength decreases. We know that the lowest wavelengths are going to be, around the 400 to 450 nanometer range. Those are purple. So we're going to see that if you have high splitting energy, those complexes are going to be kind of yellow-orange, somewhere in that color range. These will appear orange or yellow because the high energy blue-purple light is being absorbed, and so we're going to see orange-yellow as a result. We're going to see that lower ones might absorb red. If they absorb red, we'll say maybe that's 700 nanometers. That's red light. If they absorb red, these will appear green to us. And so we're going to see that it's all, it's a series, right? That's why it's called a spectrochemical series. Spectro referring to light. And so we're going to see that we have these different colors based on these splitting energies. And so it just kind of depends. The lower one, you're going to see more kind of green colors. You're going to see more blue colors as a result because the lower energy lights will be absorbed. With the higher complexes, you're going to see more oranges and yellows because the higher energy ones are going to be absorbed. So I know it's a lot of opposites here. So that's why these things appear, these vibrant colors, is because we're absorbing other areas of visible light. So, cool. Do I want to continue this? So this has all been for octahedral stuff. Actually, I think this is going to be a good place to stop because tomorrow we'll talk briefly about square planar and tetrahedral ones because they're going to have different splitting patterns. because they have different shapes. Oh, I know what I should do. I should show you d orbitals crystal field theory. Let's see if we have good examples of this. Yikes. Why do these like horrible pictures come out? Ugh. Okay, well, whatever. Back to Google for us. So if we, this is like the most low, okay. So if we pretend our ligands are these little dots on the outside of our octahedron, this is apparently how we draw an octahedron, by the way. If we see the lower energy ones, they're kind of in between the dots. All of these lower energy orbitals are in between the dots. And our higher energy ones are the ones that are going to end up lining up with the dots. So they're going to be very close to touching them here. So we're going to see that these two end up being our high energy orbitals. And these three end up being our low energy orbitals for octahedral complexes. We're going to see for tetrahedrons, it's going to be the opposite. And then for square planar, we're going to have a whole different system to look at. Actually, this one might have, let's see, will we have, nope. Okay, well, I tried. So, suffice it to say, there are lovely pictures of octahedra there that we can see. So you see that these higher energy ones interact with the ligands. The lower energy ones do not. They have nice space in between them. So, alrighty. I will put up your homework. I guess I should do that. This stuff I don't think is on your final, so you can probably get rid of it. But once I put the practice final up, I'll know for sure. So don't dump it out of your brain just yet. Tomorrow we'll finish off with the other two shapes that we see for complex ions, and then we can start nuclear chemistry. So hooray! I will make this homework due later than normal just because there's no rush on it. You don't have an exam on this coming up. So, all right. See you tomorrow then. Sorry about the technical problems, but I'm glad we were able to solve them. So, hooray.